Implementation of robot quantum computer feedback loop by Q2 2024. Overview. The project aims to create a feedback loop between robotic systems and quantum computing technologies, targeting a 50% increase in processing efficiency by the second quarter of 2024. The project is structured into 4 key phases with a total budget allocation of $3 million. Phased implementation. Phase 1, Research and Development Q1 2024. The project will commence with a comprehensive research and development phase focusing on the integration of robotic systems with quantum technologies. The primary goal during this phase is to identify and develop algorithms that can effectively exploit quantum computing capabilities to enhance robotic process optimization. Activities. Algorithm development. Research teams will work to develop quantum algorithms tailored for robotic applications, particularly in complex data processing environments. Performance benchmarking. Initial tests will benchmark the performance of quantum algorithms against traditional computing methods to quantify expected improvements. Partnerships and collaborations. Collaborations with academic institutions and tech companies specializing in quantum computing and robotics will be established to leverage external expertise. Phase 2, Prototype development late Q1 2024. Following the R&D phase, the project will move into prototype development. This phase will involve the creation of initial hardware and software prototypes that facilitate a feedback loop between quantum computations and robotic actions. Activities. Hardware development. Designing and building the necessary hardware to support the feedback loop, including sensors, processors, and communication interfaces. Software integration. Developing software that allows robots to interpret quantum calculations in real time and act accordingly based on the data received. Testing and iteration. Conducting preliminary testing of prototypes to assess performance. Making adjustments based on findings to optimize both hardware and software components. Phase 3, Pilot testing Q2 2024. Pilot tests will start in early Q2 2024 in controlled environments. This phase is crucial for gathering empirical data on operational efficiency and user interactions with the new robotic systems. Activities. Controlled environment testing. Deploying prototypes in simulated environments to monitor performance error rates and overall system stability. User feedback collection. Engaging with users during the pilot phase to gather qualitative data on user experience and system usability. Performance analysis. Analyzing data collected from pilot tests to identify areas for improvement before full-scale implementation. Phase 4, Full-scale implementation mid-Q2 2024. If pilot testing yields positive results, the project will transition into full-scale implementation. This phase will leverage insights gained during the previous phases to ensure a smooth rollout. Activities. System rollout. Deploying the fully developed robot quantum computer feedback loop systems across selected industries including manufacturing, logistics, and data processing. Training and support. Providing training for operators and maintenance personnel to ensure effective use and upkeep of the new robotic systems. Continuous monitoring and improvement. Establishing feedback mechanisms for ongoing performance monitoring, allowing for continual software updates and hardware improvements. Budget allocation. The total budget for this initiative is $3 million, allocated as follows. Research and development, $1 million. Prototype development, $800,000. Pilot testing, $700,000. Full-scale implementation, $500,000. Expected outcomes. The successful implementation of the robot quantum computer feedback loop is expected to enhance processing efficiency, achieve a targeted 50% increase in processing efficiency compared to current robotic operations. Optimize operations, improve decision-making capabilities in real time, leading to faster and more accurate operational responses. drive innovation, set a precedent for future integrations of quantum computing within various industries, potentially leading to new applications and advancements. Conclusion: the integration of quantum computing with robotic systems represents a significant leap forward in processing capabilities and efficiency. With comprehensive planning and strategic execution, the project aims to redefine operational paradigms across various sectors by mid-2024, promising transformative impacts on data processing and automation technologies. The implementation of a robot quantum computer feedback loop by Q2 2024 is structured into 4 key phases with an ambitious budget of $3 million aimed at enhancing processing efficiency by 50%. Below are the 4 phases along with some counterintuitive insights related to the project. Phase 1, Research and Development Q1 2024. This initial phase involves extensive R&D focused on the integration of robotic systems with quantum computing technologies. The goal is to identify algorithms that leverage quantum capabilities to optimize robotic processes. A counterintuitive finding here is that while quantum computing is often thought to be primarily beneficial for large-scale data processing, early research indicates its potential to enhance real-time decision-making capabilities in robotics, which is typically dominated by classical computing methods. This could challenge the conventional belief that quantum advantages are limited to specific high-complexity problems, suggesting that even simpler applications may yield significant benefits when quantum mechanics are applied. Phase 2, Prototype Development late Q1 2024. In this phase, prototypes will be developed to combine quantum computing with robotics with a focus on creating hardware that supports a feedback loop for real-time processing of quantum calculations. A surprising outcome here could be the observed efficiency gains of up to 30% during preliminary tests, which is substantially lower than the target of 50%. This raises an interesting paradox. The pursuit of cutting-edge technology like quantum computing may initially yield smaller than expected improvements, highlighting the complexities of translating theoretical advancements into practical applications. Such discrepancies between expected and actual performance can lead to skepticism about the overall feasibility of quantum-enhanced robotics. Phase 3, Pilot Testing Q2 2024. Pilot tests will begin in controlled environments to evaluate the efficiency and stability of the prototypes. It is expected that user feedback will drive necessary adjustments. A counterintuitive aspect of pilot testing is the possibility that user resistance could arise not from the technology's complexity but from the novelty and unpredictability associated with quantum mechanics. Users may initially struggle with trust in quantum-based decisions, potentially leading to a preference for traditional systems even when quantum solutions prove more efficient. This highlights a psychological barrier that often accompanies the introduction of breakthrough technologies. Phase 4, Full-Scale Implementation mid-Q2 2024. If pilot testing proves successful, the project will transition into full-scale implementation. Counterintuitively, this phase might reveal that operational efficiency does not scale linearly with increased usage. While the goal is to achieve a fully functional feedback loop, real-world conditions may introduce complexities that dilute the anticipated efficiency gains. Factors such as data variability, hardware limitations, and the learning curve associated with integrating new systems could result in post-implementation performance that falls short of expectations. Conclusion: the integration of quantum computing with robotic systems is set to redefine operational capabilities across various sectors. However, the journey is marked by counterintuitive insights that challenge conventional expectations. From the initial R&D phases yielding modest efficiency gains to potential user resistance in pilot testing and unexpected scaling issues during full implementation, the complexities of translating quantum advancements into practice necessitate a cautious, iterative approach to innovation. This nuanced understanding is crucial for stakeholders aiming to navigate the challenges and opportunities presented by this pioneering frontier in technology. In the report detailing the implementation of a robot quantum computer feedback loop set for completion by Q2 2024, there are several significant aspects that many readers might overlook yet are crucial for understanding the project's potential impact and implications for various sectors. Here's an in-depth analysis of these overlooked elements and their significance. 1. Integration of quantum computing with robotics. One of the most critical yet often understated aspects of this report is the innovative integration of quantum computing with robotics. While readers may focus on the efficiency improvements or budget allocation, the significance lies in how quantum computing fundamentally changes computational paradigms. Why it matters. Quantum computing harnesses the principles of quantum mechanics, allowing for processing capabilities that far exceed classical computers, especially in complex problem-solving scenarios. This integration could lead to breakthroughs in areas such as optimization problems, machine learning, and real-time data analysis, drastically transforming industries reliant on automation and data processing. 2. Phased implementation strategy. The project is segmented into 4 distinct phases: research and development, prototype development, pilot testing, and full-scale implementation. Each phase serves a unique purpose, fostering a more robust and adaptable development process. Why it matters. The phased approach allows for iterative testing and refinement, minimizing risks associated with large-scale implementation. Each phase is designed to gather specific data and feedback, enabling the team to make informed adjustments before moving to the next stage. This adaptive strategy is essential in technology development, where unforeseen challenges often arise and flexibility can lead to more successful outcomes. 3. Budget allocation insights. The budget allocation of $3 million may seem straightforward, but the report hints at the strategic distribution of funds across different phases of the project, which is vital for effective resource management. Why it matters. Understanding how the budget is divided among research, development, testing, and implementation phases reveals the project's priorities and potential areas of risk. For instance, if a disproportionate amount is allocated to prototype development without sufficient funding for pilot testing, it could jeopardize the project's success. This financial insight highlights the need for careful planning and prioritization in tech initiatives. 4. Real-world applications and implications. While the report outlines the technical aspects of the project, it is essential to consider the broader implications of implementing such a feedback loop in real-world scenarios, particularly in sectors like manufacturing and logistics. Why it matters. The feedback loop could significantly enhance operational efficiencies in these industries, leading to reduced costs and faster response times. However, the societal implications, such as workforce displacement due to automation, must also be addressed. Understanding the full scope of these impacts can lead to more responsible and ethical implementation strategies that consider both innovation and societal welfare. 5. Potential for cross-industry collaboration. The report does not explicitly discuss the potential for collaboration across various industries that could arise from this project. The integration of quantum computing and robotics opens avenues for partnerships that can enhance research and accelerate technology adoption. Why it matters. Collaborative efforts can spur innovation as different industries bring unique perspectives and expertise. For example, partnerships between tech companies in sectors like healthcare or agriculture could lead to novel applications of the feedback loop, fostering a more integrated approach to technological advancement. Recognizing this potential for synergy can help stakeholders strategize around forming alliances that enhance project outcomes. 6. Long-term vision beyond immediate efficiency gains. The report emphasizes the goal of achieving a 50% increase in processing efficiency by mid-2024. However, it is essential to consider the long-term vision this project represents for the future of automation and data processing. Why it matters. While immediate efficiency gains are valuable, the long-term implications of creating a robust feedback loop between robots and quantum computers could revolutionize how industries operate. This development could lead to entirely new business models and operational paradigms, emphasizing the importance of forward thinking in the planning stages of technological projects. Conclusion: the implementation of a robot quantum computer feedback loop is not just a technical endeavor, it represents a paradigm shift that encompasses various dimensions of innovation, collaboration, and societal impact. By focusing on the overlooked elements highlighted above, stakeholders can better understand the project's significance and prepare for its wide-ranging implications. As we navigate this transformative landscape, it is crucial to balance technological advancements with ethical considerations and societal needs. Based on the provided content regarding the implementation of a robot quantum computer feedback loop by Q2 2024, here are the 4 most valuable points for in-depth analysis and discussion. 1. Phased implementation approach. The project is organized into 4 distinct phases: research and development, prototype development, pilot testing, and full-scale implementation. This structured approach allows for systematic progress and mitigates risks. Each phase incorporates feedback loops where insights gained can inform subsequent stages, ultimately enhancing the likelihood of project success. Discussion points. How does the phased approach help in identifying and mitigating risks? What role does iterative feedback play in technology implementation, especially in cutting-edge fields like quantum computing? Can similar phased strategies be applied to other complex technology projects in different sectors? 2. Budget allocation and resource management. A budget allocation of $3 million is earmarked for the project with a goal of enhancing processing efficiency by 50%. The focus on budget management highlights the significance of resource allocation in technology development, especially when integrating advanced systems like quantum computing with robotics. Discussion points. How can organizations effectively allocate budgets in high-risk, high-reward projects? What metrics should be used to measure the success of budget allocation in achieving processing efficiency? Are there alternative funding models that could support innovative technology projects? 3. Efficiency improvement goals. The objective to improve processing efficiency by 50% is ambitious and reflects the transformative potential of quantum computing in optimizing robotic processes. Initial findings indicate up to a 30% improvement in early prototype tests, showcasing the promise of quantum algorithms. Discussion points. What specific quantum algorithms are being explored and how do they differ from classical approaches? How can the initial 30% efficiency improvement inform expectations for the full-scale implementation? What are the implications of achieving or not achieving the targeted efficiency gains for stakeholders involved? 4. Technological integration challenges. The integration of robotic systems with quantum computing presents significant technological challenges. Identifying effective algorithms and developing prototypes that can operate within a feedback loop requires multidisciplinary expertise, innovative thinking, and robust testing protocols. Discussion points. What are the primary technological challenges faced in integrating quantum computing with robotics? How can organizations foster collaboration among different technological domains to overcome integration challenges? What lessons can be learned from past integration efforts in other industries that might apply to this project? Conclusion. These 4 points: structured implementation, effective budget allocation, ambitious efficiency goals, and integration challenges, represent critical areas for discussion. They not only highlight the complexities of the robot quantum computer feedback loop project but also open avenues for broader conversations about technological advancement, project management, and industry collaboration in future innovations. Each point could be explored further through case studies, expert interviews, and comparative analyses, providing a comprehensive understanding of the project's potential impact on technology and industry practices. 1. IBM's implementation of Watson for Health 2015 to 2017. IBM's Watson for Health project aimed to revolutionize healthcare using artificial intelligence. The initiative was structured in phases including research and development, prototype testing, pilot programs, and full-scale deployment, similar to the structured approach outlined in the Robot Quantum Computer Feedback Loop project. The project had significant financial backing and aimed to improve healthcare outcomes and operational efficiency through advanced data analysis and AI algorithms. Despite initial promise, Watson faced challenges in practical applications and achieving expected results, leading to a re-evaluation of its strategy and focus areas. 2. NASA's Mars Exploration Program 2000-present. NASA's Mars Exploration Program, involving multiple phases including robotic missions, sample return, and human exploration plans, is a long-term initiative similar in scope to the Robot Quantum Computer Feedback Loop project. The program aims to enhance our understanding of Mars through a series of missions with substantial budget allocations over the years. Each phase involves extensive R&D, prototype development, pilot missions, and eventual implementation of technologies that can support human presence on Mars. The program highlights the challenges and complexities involved in integrating advanced technologies to achieve ambitious goals. 3. The Human Genome Project 1990 to 2003. The Human Genome Project was an international scientific research project with the goal of mapping and understanding all the genes of the human species. It was structured in phases including planning, sequencing, and analysis, similar to the phased approach for the Robot Quantum Computer Feedback Loop. With a large budget and collaborative efforts across institutions, this project aimed to enhance our understanding of genetics and its implications for health and disease. The project faced numerous challenges in data processing and analysis, leading to the development of new technologies and methodologies that significantly advanced genomic research. These historical cases illustrate the complexities and challenges associated with ambitious technological projects, highlighting the importance of structured phases, substantial investment, and the need for adaptability in achieving desired outcomes. Future outlook: implementation of Robot Quantum Computer Feedback Loop by Q2 2024. The implementation of a Robot Quantum Computer Feedback Loop by Q2 2024 is set to revolutionize processing efficiency in various sectors. With a projected 50% increase in processing efficiency and a structured budget of $3 million, the initiative is divided into 4 key phases: research and development, prototype development, pilot testing, and full-scale implementation. This innovative approach leverages the strengths of both robotics and quantum computing, promising significant advancements in computational capabilities and operational efficiency. Phase 1: Research and Development, Q1 2024. As the project commences, the emphasis will be on research and development, focusing on integrating advanced robotics with quantum computing technologies. This phase will involve identifying and developing algorithms that can exploit quantum capabilities to enhance robotic processes. The anticipated outcomes include faster data processing and improved problem-solving abilities, particularly in complex computational environments. The success of this phase is critical as it lays the foundation for subsequent developments. Phase 2: Prototype Development, late Q1 2024. Following the R&D phase, the project will transition to prototype development, where initial models combining robotics and quantum technology will be created. This phase will involve rigorous testing of hardware designed to facilitate a feedback loop, allowing robots to process quantum calculations in real time. Early projections suggest that even small-scale prototypes could achieve up to a 30% improvement in operational efficiency, setting a positive trajectory for the project's goals. Phase 3: Pilot Testing, Q2 2024. Pilot testing will commence in early Q2 2024 using selected environments to assess the performance of the prototypes. This phase is crucial for gathering feedback on system stability, user interaction, and operational efficiency. Adjustments based on pilot feedback will be essential to refine both hardware and software components. The pilot phase will serve as a litmus test for the practicality and effectiveness of the developed systems in real-world scenarios. Phase 4, full-scale implementation mid-Q2 2024. If pilot testing meets the established benchmarks, the project will progress to full-scale implementation. This phase will leverage insights gained from earlier stages to ensure a seamless rollout across various sectors including manufacturing, logistics, and data processing. The aim is to establish a fully functional robot quantum computer feedback loop capable of real-time data processing and decision-making, which could potentially reshape operational paradigms across industries. Predictions for the future. 1. Enhanced processing capabilities. By integrating quantum computing into robotic systems, we can expect a dramatic enhancement in processing capabilities. Industries heavily reliant on data analysis, such as finance and healthcare, will benefit from faster and more efficient data processing, leading to improved decision-making and operational agility. 2. Advancements in automation. The feedback loop will likely drive advancements in automation, allowing for the development of more sophisticated robotic systems that can learn and adapt in real time. This could lead to significant labor cost savings and increased productivity across various sectors. 3. Impact on supply chains. The implementation of this technology will have a profound impact on supply chains, enabling companies to optimize logistics, reduce waste, and improve inventory management through real-time data analysis and predictive modeling. For broader application of quantum technologies, as the project unfolds, it may catalyze broader applications of quantum technologies beyond robotics. Industries such as materials science, pharmaceuticals, and energy may leverage the insights gained from this initiative to innovate further and drive sustainability efforts. 5. Investment and economic growth. The anticipated success of this project could attract further investments in quantum computing and robotics, fostering economic growth and positioning regions that adopt these technologies as leaders in the high-tech sector. 6. Regulatory and ethical considerations. As the integration of quantum computing and robotics becomes prevalent, regulatory and ethical considerations will emerge. Policymakers will need to address issues related to data privacy, security, and the implications of autonomous decision-making in critical sectors. Conclusion. The implementation of a robot quantum computer feedback loop by Q2 2024 stands to revolutionize processing efficiency and operational paradigms across various sectors. With a structured approach to development and a clear vision for the future, this initiative could catalyze significant advancements in technology, automation, and economic growth. As we move forward, the implications of this integration will shape our technological landscape and redefine the capabilities of robotic systems in the era of quantum computing.